show a short presentation first. This will take about 20 minutes, and then afterwards I would like to demonstrate a couple of features in this release as well using the LedaFlow GUI. Okay, so the contents of this presentation. So I will say something about the inline separator. A couple of things about wax deposition improvements. There are about 5 improvements that are worth mentioning in version 2.3. Then some other model improvements, including for composition tracking and heart rate margins. And then a couple of new things in the GUI, the device boundary chart, which is a new feature, and some improvements to the parametric studies. And then finally the demonstrations. So the inline separator in LedaFlow. So before version 2.3 we also had a separator, but it was only an end-of-line separator. So it was only possible to have a multi-phase line going into a separator, and then it was not possible to connect anything to the outlets of this separator tank. We have changed the model. So right now it is possible to add outlet pipes, and the main use case for this is to do subsea separation, which is we got a lot of requests from customers about that. Also, it is we've implemented it in a way that is completely flexible, so it is also possible to use it for other cases, like for instance having a 2-stage separation. Now I'll show both of these examples in the demonstration afterwards as well. We support any kind of PVT except for single components like pure CO2 and steam, but all the other PVT methods like black oil, PVT tables, or multi-flash with composition tracking, that is all supported. And as part of this development, we've improved a couple of other things as well. It is now possible to have different head shapes, so not just the flat heads that we used to have, but now you can also have elliptical or other head shapes. So this makes the geometry of the separator much more realistic. And then yeah, finally we've capped this off with a new GUI design, so it's a bit easier to find things. It's a bit more organized, is where you put in the settings for the separator. Okay, so that's not a lot of text, but I can assure you that a lot of work has gone into this. It was yeah, the biggest development that we have for version 2.3. The other main thing that we worked on for this release are the wax deposition improvements, and there are a bunch of improvements that are important there. So the first one, it is related to the interpolation of the precipitation curve. The wax precipitation curve, it gives you the wax fraction as a function of temperature. So when the temperature drops, you get more wax precipitation, and also so you get more wax particles in the oil, but also more wax particles sticking to your pipe wall. And then what we found out was that the interpolation of these of this precipitation curve, which is entered as a table of values by the user, the interpolation has quite a big effect on the accuracy of the wax deposition model. So previously we were using linear interpolation, that is the black line showing here. So it just goes as a straight line between the points. But in reality this should be a smooth curve. So what we've done in this version is to use a spline in order to get a smooth interpolation of this curve. And that results in a much greater accuracy, and also the wax layer thickness profile is now smooth. So I will show this during the demonstration what exactly how exactly the results have changed as a result of this. Then there were some issues with the pressure drop effect. So when the wax deposits on the pipe wall, then the surface area of the pipe, or the pipe diameter, it effectively gets smaller. And then because of that, the pressure drop through the pipe increases because of the higher velocity of the fluid. So this was not working properly, and it has been fixed now. So you can now see a effect when the wax deposits on the pipe wall, then the pressure drop increases, which is what you would expect. And also we've implemented a non-Newtonian wax slurry rheology. So we're using the Pedersen model, which is what is used in PVT sim when characterizing your wax, so your waxy oil. So that is what is shown over here in the wax deposition settings. It's now possible to choose the viscosity model. So we have two options there. The Thomas model, which is the Newtonian option that we had before. And also you can now choose the Pedersen model, in which case you give these D, E, and F coefficients. They are multipliers that come from PVT sim. So if this multiplier is, so if it's set to 1, like in this case, then basically you're using the standard Pedersen model. But yeah, depending on the oil that you're using, they can be a little bit different from 1. But it should be in the same, in the order of magnitude of 1 at least, these values. Then the fourth improvement that we made is with the wall roughness increase. So it is now possible to have an increase in wall roughness when the wax deposits on the pipe wall. And by default, this option is turned off because we're not entirely convinced that for any kind of wax this is important. But in some cases, you might get a rough wax deposit on the pipe wall, and this could, in principle, increase the wall roughness that the fluid experiences. So that's why we've added this advanced option. So it's by putting a coefficient here, this is how much the wall roughness you get. So for instance, if this wall roughness increase is set to a factor of 1, it means that 1 millimeter of wax deposit gives 1 millimeter of wall roughness. So it's kind of like a multiplicative tuning coefficient. But by default it's set to 0, so then it doesn't do anything. The last thing that we did is we now have the option for the pig that you send through the pipe. The pig now removes the wax deposit. So the wax deposit is scraped off, but we don't track these chunks of wax that are formed and pushed forward by the pig. So it is a way of removing the wax deposit, but we don't have a viscosity model that can do anything with this wax deposit that is scraped up. So this is why we don't track it any further in the simulation. So it's only a method, it's only a way of removing the wax deposit, and then the wax deposition process will start all over again. Some other model improvements that are worth mentioning. So for the hydrate inhibitors and custom fluids, the viscosity mixing rule for MEG, methanol, and ethanol has been adjusted. So previously, particularly the mixture viscosity of concentrated MEG was too high. So this happened when the glycol fraction was above 50%, for instance. And then what we've done now is added one additional parameter in the viscosity mixing rule, which allows us to adjust for non-ideality, which is particularly important for these polar molecules that all of the hydrate inhibitors are. So that has been adjusted, and then this parameter has been set for all the hydrate inhibitors that come as standard with LedaFlow. So it's possible to adjust this as a user, but it's not necessary because we've already done that based on comparison against Multiflash. Another thing is that we've added salt as a custom fluid, which enables us to track the salt fraction along the pipeline. So it's the reason for doing that is that we found out that it's not sufficient to put salt in just in the PVT table, because yeah, things can happen to the salt concentration. So water can evaporate or condensate along the pipeline, and then the salt fraction, it changes along the pipe. So in our opinion, it's better to model the salt as a custom fluid, because then you know the change in salt concentration along the pipeline. And then this has an important effect on the hydrate margin. Even a couple of % of salt, it acts as a very good hydrate inhibitor. So that's why we would want to model the salt. And then in LedaFlow 2.2, we already had the option of using salt as a heart rate inhibitor in the Hammersmith equation. So yeah, the Hammersmith equation itself has also been extended. So we're still using the same model, but we've just expanded it so that it can handle mixtures of inhibitors. So for instance, you can have salt and monoethylene glycol in the same water phase, and then LedaFlow computes the combined inhibitive effect of both of these inhibitors. So that way you can be less conservative on your heart rate inhibition, because it takes into account not just the heart rate inhibitor, but also the salt that may come with your production fluids. Also, as a side effect, it's now no longer necessary to select a specific inhibitor for the Hammersmith equation. It just looks at what custom fluids or composition is in your flow, and it uses all of the inhibitors by default for calculating the heart rate margins. So it will automatically be taken into account. Yeah, then something completely different. In composition tracking, we've made an adjustment so that for choke valves, so when the valve is partially open, we now flash the fluid that is going through the valve. And then the reason for doing that is that because of the high pressure drop over a choke valve, there can be a lot of mass transfer, like condensation or evaporation. And then the standard mass transfer term that we have for composition tracking, it was not giving fast enough mass transfer. So now we're doing a pH flash to remedy that, which basically means that we're assuming that the fluid is fully mixed in the valve body, which I think is reasonable for choke valves. Yeah, that concludes the model improvements. So we also have a couple of improvements on the GUI side to make LedaFlow easier to use. So there's a new feature called the device boundary chart, which is a graphical way of showing time varying inputs, like the flow rates, temperature, pressure, valve opening fraction, and leak diameter. And then yeah, just to show an example, this is what happens for a case where there's a leak in the pipeline. You can see here in this top plot over here that after 1,000 seconds simulation time, the leak opens. So this is to simulate a real leak in the pipeline. And you can see after that there's something happens to the wellhead chokes, which are located over here. They both close, and also the gas lift sources in the well, they both are shut down as well. And then after a while, the pipeline in this case is depressurized. So the whole idea behind this feature is to correlate the time dependency of different input parameters to make it possible to quality assure a model before you have to run it. So it's very often in shutdown cases where you have to do a sequence like closing valves, closing sources, and then using this feature, it's easy to make sure that this sequence is set up correctly. So it makes it much simpler to do it to do the simulation in the correct way the first time. I can also mention here that we're only showing the time-dependent input for this in these plots over here. And the reason for that is that if you have a very large model, then showing all of the constant inputs would just clutter up these plots over here. So we've limited it only to the time-dependent variables. And then when you modify your model, these are automatically updated whenever another variable becomes time-dependent or if it's removed. So this plot, you can have it open while building your model, and it will be dynamically updated. Then the parametric study improvements. So the main focus here was on making it more user-friendly. So in order to do that, we've improved the input parameter selector. So this is shown here on the right. So it's much easier now to find the right object that you want to do a parametric variation on. And also, yeah, you can see the base case values over here. So it's much easier to see what you're actually trying to do. So that is for selecting the input parameters. Second thing we've changed is we've cleaned up the parametric table as well. So the rows here, they take up less space, so it's a bit more compact for large parametric studies. And the column headers, they are now divided over multiple lines. So you can see here that it's much easier to find what this variable means now, because the first line, it shows the logger name, in this case the pipe and the trend. Then there comes the variable and then the qualifier for it. So in this case you can see this is the total pressure drop as opposed to the gravitational and frictional pressure drop for this pipe. It makes it a bit easier to see what is here. Yeah. Also fixed a couple of bugs that in some cases it was possible to if your PC was very busy, it was possible for these single values, these results, not to be calculated properly. So it was just showing blanks. And then this has been improved. And we've tested all the possible inputs that you can set in a case, and then resolved any issues related to that as well. Okay, then we go and get to the demo part of this presentation. So I would like to show some of the new sample cases, as well as the improvements we've made to the existing sample cases. And then I would like to show the capabilities of the inline separator, and finally the wax deposition improvements. Okay, so if you open the LedaFlow GUI, then if you right click anywhere in the case browser, then you can select new case. And then if you click on the sample cases tab, this is where all our sample cases are located. So we've changed the formatting here a bit. So the names are still more or less the same, but we're now showing keywords over here, which makes it easier to find a sample case that fits what you're interested in. So for instance, here you can see that if you want to know about turn-down curves, then you need to take this case. Another case that looks at corrosion and different things. So it's much easier to find different sample cases now. So let's just try to open this one. So now we get the sample case, and you can see that it automatically opened the notes tab of the status view over here. So this is where we give a description of this case, and also what to do in order to look at the simulation results. All of the sample cases now have this description, which is very useful, and with this you can easily work with all these sample cases yourself. I can also add that some of the sample cases, they have parametric studies attached. So for instance, this case has a turn-down parametric study. And then this turn-down, it has its own description here in the notes page as well. So each of these parametric studies has a different description, because the parametric studies, they do different things. Yeah, those are the sample cases. It's very interesting if you have a bit of extra time to have a look at that. Then I would like to show the inline separator. So this is the plot, this is a picture that you've already seen in the presentation. I just want to show what you can do with this. So this is a subsea separation case. So there's a relatively short multi-phase pipeline that is feeding into the separator on the seabed. And then there are two pipes. One pipe is feeding the liquid to the top side. So this consists of a 30-kilometer flow line with a 1 kilometer high riser, and the same for the gas pipe. And then the whole idea behind this subsea separation for this particular case is to be able to do the boosting for the liquids only. So if you had one big multi-phase pipeline going to the top side, then we would have to have a pump that can handle all the gas that is going through it. But by separating it subsea over here, then we can just use a pump to pump the liquid to the top side, and the gas, it just flows naturally. So in this way, there's quite a lot of cost saving possible by just boosting the liquid rather than multi-phase flow, because true multi-phase pumps are quite expensive. Okay, so I've already run this case, so we can have a look at some of the results actually. So this is showing the results for the pump. You can see here that initially the pump it's not moving, so it's at 0 RPM. Then during 2 hours of simulation, the speed is ramped up until it reaches 2000 RPM over here. And then during this time, there's some the pressure boost also increases. So while ramping up the pump, and then you can see it goes up and down a bit over here, and that is because we're using pump curves for this pump. So it's not just pump speed that has an effect on the pressure boost, but also the gas fraction and some other parameters. And then in the end, it stabilizes at about 40 bar pressure boost. And you can also look at other things here. So this case is based on a sample case. So if you want to know more about it, it's possible to replicate this later. Then this is showing what happens in the liquid pipe, which is boosted. So you can see the pressure, it goes up here. This is at the location of the pump. And if we look at it from the start of the simulation, we can see that initially there's quite a lot of gas, about 90% in the pipeline. And then after running the simulation for a while, the gas is transported out. And then in the end, there is only maybe 10% or 5% gas around the location of the pump, which is quite okay. Yep. And then this is showing what is happening in the separator. So this separator, it is configured as a two-phase separator. So we're just separating the gas from the liquid, but not the oil from the water. So you can see here that it's pretty much at steady state all the time. The interface height, it varies only very little. It would probably be possible to improve this even further by tuning the controllers a bit, but I'm quite happy with this performance. So we can see that the pressure is almost constant, and also the interface height is almost constant in the separator. So this is working well. Yes, another application of the inline separator, it's possible to do two-stage separation. So it's maybe not so relevant for subsea cases, but if you want to simulate the top sides in detail, then it's possible to do that now. So you can have a high pressure separator and a low pressure separator, feeding the gas into a high pressure and low pressure network. And then the liquid is just fed into one liquid pipe over here. So it's possible to make it three-stage as well, but I haven't done that now. But there's a lot of flexibility in a separator model, so you can do basically anything you like now with it. Then for something completely different, so the interpolation for the wax deposition. So I will just show you what this precipitation curve looks like that we already talked about. So in this case, I have very few points for my precipitation curve. So it's only a point at 40 degrees Celsius, 20 degrees, and 0 degrees Celsius. So you can see that it's very crude if you use linear interpolation, like over here. Then I've done a comparison between LedaFlow 2.2, which has the linear interpolation, and LedaFlow 2.3, which has the smooth spline interpolation. And then I can show you the difference that it makes to the wax deposition. So first of all, in version 2.2, we can see that there's these strange bumps in the wax deposition rate along the pipe. Well, this is not the wax deposition rate, but the wax layer thickness. So you can see here is where the wax starts to form. And you can see it goes up and then it goes down again, and then it goes up again. And this is because of the change in the inclination of this precipitation curve. So you can see it more clearly in the fraction of wax in the oil. So these are the wax particles in the oil phase. You can see that it has this imprint of the linear interpolation. So it goes up like this, and then it goes up like that. So this is because here this is where the temperature reaches this point in the interpolation. So probably it's around 20 degrees Celsius here, and this probably corresponds to 40 degrees Celsius. Now in version 2.3 with the smooth interpolation, we can see that the point where the wax starts to form, it's a lot later in the pipeline, and then there are no strange bumps in the wax layer thickness anymore. So this is much more accurate. And it's even more clear if you look at wax volume fraction in the oil phase. Now it's completely smooth. There are no strange bumps there from the interpolation anymore. So this works nicely. And depending on the case that you're simulating, this is this may even have an effect on the total amount of wax that is formed, but that depends on the temperature and other factors in your case. So we've seen cases where the amount of wax formed can be 3 times less than in version 2.2, but it really depends on what your precipitation curve looks like. Okay, that's the interpolation for the wax deposition, but we've also changed the viscosity model and would like to show you the effect that makes. So it's I can show you the input first. So it's possible to choose between the Thomas and the Pedersen model over here in the wax deposition settings. And then I've simulated them with the default parameters now. So this is how it works in LedaFlow out of the box. And I've done 2 simulations that I've compared. So this is what it looks like. So the wax layer thickness over here, it's very similar between the two. So apparently in this case, it doesn't really matter that much if you're using a non-Newtonian Pedersen model or a Newtonian Thomas model. So you can see there's maybe between 0 and 20% difference in the wax layer thickness. And then we can also see here that the oil viscosity is not really affected much by the presence of wax particles, and the reason for that is that there's only about between 0 and 1.5% of wax by volume in the oil phase, so that there's just not a whole lot of wax slurry. So the effect would be more significant if you have higher wax fractions.